Hello there, geometers. This is that we find when we're dealing with circles. And that type of angle is an inscribed angle. So now first off, before we get into what an inscribed angle is, let me remind you of the other type of angle that you've generally talked about. And that's not the best circle, sorry. But the other type of angle you've generally talked about, angle, is an angle whose vertex is at the center of the circle. So like it could look like this maybe, or let's say that's about maybe 100 degrees. And the thing about a central angle is whatever the measure of the arc that goes with it, it's the same for the angle. So the angle would be that there. And the arc, we call it the intercepted arc. If you were to intercept a pass in football, then that pass would go basically between your arms. That would mean your arms close in on that ball as it's going through the air. So we could think of this as like the arms of the angle. And in between them, the part that's in between them is the intercepted arc. Okay, so intercepted arc here is a concept that goes with angles and circles. We need to know what the intercepted arc, it's like it's the part of the circle that's sort of chopped off by those two arms of the angle. So an inscribed angle is formed by two chords that intersect at a point on the circle. So the key thing there is the on the circle. For a central angle, the vertex is at the center of the circle. Let's go ahead and write that. The vertex is at the center. Whereas for an inscribed angle over here, the vertex, point B, is on the circle itself. Remember, on the circle means sort of on the perimeter there. The circle itself is this, is the ink that goes all the way around. We don't consider that the outside or the edge of the circle. It is the circle. Okay, so the inscribed angle here would be angle, there's one side, there's the other side, angle ABC, or we could call it angle CBA. Either way, that's an inscribed angle because its vertex, point B, is on the circle. Now, an inscribed angle also intercepts an arc. And you notice one of the things I'm doing here is I'm tracing the two edges of it and carrying on past the edge of the circle, the two sides of the angle, and going past the circle to point out that it chops off a piece of the circle between the two sides of the angle. And in this particular case, the piece it chops off is arc AC, and that's why AC is our intercepted arc. All right, so that's the definition of an inscribed angle. Sorry, I'm having some focusing issues here. There are four sort of properties of inscribed angles. They come up quite a bit in circles. And we're going to go ahead and say that all four of those are theorems because we could prove them. So that's the next thing we're going to get into is 4 theorems. The first theorem is about its measure. Now we talked about here a central angle, the angle measure and the arc measure are the same. That's not the case for an inscribed angle. I'm going to consider this sort of theorem 1. That's just for our purposes in this video. It's not like an official name. If an angle is inscribed, then its measure is half the measure of its intercepted arc. So for instance here, if this arc measured 100 degrees, then angle ABC would not measure 100 degrees because it's not a central angle. It's an inscribed angle. It would measure half of that. Okay? Now keep in mind, it works both ways. Is you can think of it as if the angle is half the arc, then the arc is twice as big as the angle. And sometimes I like to write this on my paper when I'm dealing with inscribed angles is exactly what I just said. Angle is half the arc. Okay, so that might be something you do on your homework. And remember, that means the arc is twice as big as the angle. The classic example there I like to think of is if one thing is half the size of the other and the other is twice as big, like if you are half my age, then that means I'm twice your age or 2 times as old. So you really have to be able to keep it straight of which one's bigger. The bigger one here is the arc itself. The half is the angle. Okay, so here's a couple of examples using that property of inscribed angles, that theorem. and one I just did. Example 1, find the measure of angle BAC. If the arc BC, is 100 degrees, there's my angle. That's the inscribed angle, and BC is the intercepted arc, so my inscribed angle is going to measure 50 degrees. Now over here, we're given the inscribed angles measure, and we need to find the arc measure. And remember, the angle is half the arc, so that makes the arc the bigger one. The angle's the smaller one. So if this is half of this arc, and let's go ahead and trace over those to make it clear. Here's the angle. And I can't tell you if you have any problems with it, if you're having any difficulties with a problem, basically. It really is helpful to do what I'm doing and trace over the two sides and extend them so that you can see very clearly what part of the circle is between those two sides of the angle. So the arc has to be twice as big as the angle, so 10 degrees times 2, the arc here is 20 degrees. Okay, now let's look at a little bit more complex example. Here we have a triangle inscribed in a circle. And really a triangle has 3 points, but it also has 3 angles. So we have 3 inscribed angles. So I'm going to look first at angle A. Angle A, here's the vertex. There's one side of angle A. There's another side of angle A. So angle A intercepts arc BC or CB, which is 160 degrees. That means angle A would have to be half of 160 degrees, or 80 degrees. Okay, so I'm going to go ahead and write that over to the side. Maybe pause your video and see if you could find angle B, the measure of angle B. All right, so angle B, and I'm going to do this on a separate sheet of paper if I can. Let's see if I have another one. Okay, I'm looking at angle B now. There's the vertex. It's on the circle. That's what makes it an inscribed angle. Here's one side of the angle. Here's the other side of the angle. And that means angle B measures half of 90 degrees, so that's going to be 45 degrees. The reason I did a fresh drawing is because we already had angle A marked on this one, and it starts to get a little bit messy when you have several angles marked on the same picture. But let's go ahead and put in that information we had from angle A. This is now angle B is 45, and I'll put angle A over here. Now, there's 2 ways I could proceed here because I don't know angle C, and I also don't know the arc that it goes with, the intercepted arc. Angle C is right here. The intercepted arc for C is arc AB. I don't know either one. I could go about finding out what I need to know there either way. I could either look at all of the arcs have to add up to 360. So I could say, well, let's find this arc by subtracting 360 minus 90 minus 160. And I found that the arc is 110, the one I'm pointing at, which is arc AB. Then I could take half of that and get the measure of angle C. That's one way to do it. The other way is, this is a triangle, and the measures of a triangle have to add up to 180. So 180 minus 80 minus 45 gives me 55 degrees for measure of angle C. So there's that. And then angle C intercepts, and let me see if I can draw this on here. The blue angle here is angle C. It intercepts this arc, so if that angle is 55, this is 110. And so then we have finished the example 3. All right, next theorem. If 2 inscribed angles of a circle intercept the same arc, then the angles are congruent. There are really a couple of examples in this picture, so I'm going to go ahead and show you both of them. One is arc AD is intercepted by angle ABD. angle ABD. Arc AD, same arc, is also intercepted by, let's use a different color, angle ACD. Because they intercept at the same arc, they have to be the same size. Because whatever the measure of arc AD is, they're both going to be half. If the measure of arc AD was 80 degrees, this would be 40 degrees, this would be 40 degrees. So I can say the measure of, let's not even use measure, it says congruent, so let's go with that. Angle ABD is congruent to, which means same measure, angle ACD. All right, we could also turn this around and look at the fact that we have two angles that both intercept, arc BC. Let me go ahead and check that out. There we go. All right, if we're looking at arc BC, we could say that angle BDC, sorry, I traced it kind of wonky there, BDC, that intercepts arc BC, it should be the same as angle BAC, which also intercepts the same arc. They both have to be half of that arc. So BDC is congruent to BAC. All right, that's 2 theorems down and 2 to go. I did say I was going to number these, so let's go ahead and call that our second theorem, or theorem 2. And again, that's just for the sake of this video so we can refer back to stuff. So that makes our next theorem, theorem 3. Theorem 3 says an angle that is inscribed in a circle is a right angle if and only if its corresponding arc is a semicircle. So let's see what that means. From A to C, or you could call it arc ADC. That's a semicircle. That's half of a circle, which makes this angle, angle ABC, half of that. A semicircle is 180, so this is going to be 90, half of that. Another way you can look at this, a couple ways. One is anytime you have a triangle inscribed in a circle, and to be inscribed in the circle, that means all 3 points have to be on the circle. So point A is on the circle, point B is on the circle, point C is on the circle. If you have a triangle inscribed in a circle, if one side of the triangle is a diameter of that circle, then it's going to be a right triangle every single time. Because that implies that this angle over here cuts off or intercepts half the circle, and half of 180 is always 90. Okay, our fourth theorem about inscribed angles, or kind of fourth fun fact, is that you can put a quadrilateral in a circle if and only if its opposite angles are supplementary. Now, what does this have to do with inscribed angles? Well, we have 4 different inscribed angles here. Angle A is an inscribed angle, angle B is an inscribed angle, and so on. I really like looking at why this one's true because it's pretty cool. Okay, so what this means is if I pick any 4 points on a circle, I just randomly picked 4 points on my circle, and I connect them. Well, that makes a quadrilateral, a 4-sided figure, so let's go ahead and do that. No matter what quadrilateral it makes, it might make just a random one, kind of. I guess that's a one word for it. One with no special properties like the one I'm looking at right here. Could make a square, could make a rectangle, could make a trapezoid, any quadrilateral, no matter what. Then the opposite angles, meaning the ones that are sort of diagonally across from each other through the center of the quadrilateral. Not 2 next to each other, not these 2, not these 2, but let's go ahead and give it some letters and say angles A and C would be considered opposite, or angles B and D would be considered opposite. Well, they have to be supplementary. Okay, let's look at why here. Wanted to give myself a little more room there. Let's look at let's look at B and D. Here is inscribed angle B. Okay? Inscribed angle B intercepts arc AC, that portion of the circle. So that means the inscribed angle B would be half, this angle would be half the measure of whatever arc this arc is. All right. Now let's look at the one that's opposite from B. Opposite from B, cross through the middle of the quadrilateral, we get to D. Inscribed angle D intercepts this part of the circle, and so inscribed angle D is half of that arc, whatever that is. Well, look at how much of the circle I've highlighted. Together, I've highlighted the entire circle. So if the intercepted arcs together have to add up to the whole circle, which is 360, then the intercepted angles would have to add up to half of that, which is 180. Like, let's say this arc right here could be 100 degrees. Then this arc over here would be 260. Those two together add up to 360. Well, if this arc ABC, if arc ABC is 260, then angle D measures 130, half of that. If arc AC is 100, then angle ABC is half of that. And what do 130 and 50 add up to? Well, just in case you need to see the proof, there it is. They add up to 180. So that's one of the reasons I think that one's a pretty cool theorem. All right, so looking back on our paper here, that means since I have an inscribed quadrilateral here, if I need to, I could find D, because D and B have to add up to 180. So I can do 180 minus 105, and that would give me 75 degrees. Sorry, the video seems to be lagging here. I apologize for that. And if I need to find angle A, angles A and C have to add up to 180 because they're diagonally across from each other on the circle, excuse me, on the quadrilateral. These two right across here. So angle A is going to be 180 minus 85, which is 95. Now this one over here, one of the things sometimes we're asked if we're just shown a quadrilateral is, could this quadrilateral be inscribed in a circle? Could I draw a circle around through each of the vertices? And on this one, I'm going to have to say a hard no. And the reason it's a no is because these two are opposite angles and they do not add up to 180. Okay, a quadrilateral can be inscribed in a circle if and only if. That means if it can be, if it is inscribed in the circle, like in our first example here on the left, that means those angles that are opposite from each other have to be supplementary. And it also means only if the angles across from each other are supplementary could I inscribe it in a circle. And so this one cannot be. All right, so let's look at a few examples, a couple of examples here that use several of these theorems. All right, example 4 here. Okay, so example 4, and I'm sorry if the resolution's a little off. I'm trying to make the, stop being glitchy, make the video work a little bit faster here. It says, use the figure at the right to find each angle or arc measure. Okay, the first thing that I notice here is that I have a scenario that reminds me of Theorem 2. This problem looks a little bit like what we had here. And the reason it does is because we have more than one angle, two different angles intercepting the same arc. Looking at arc CD first, the one that's labeled 80 degrees, I've marked the angle. One angle that intercepts CD is angle CAD. The other angle that intercepts CD is angle CBD. So both of those angles have to measure half of arc CD, or half of 80 degrees. And one of those is angle A. So I'm going to say that measures 40 degrees, half of 80. And the other is angle B, so it also measures 40 degrees or half of 80. Okay, now, what else have we got going on here? Angle C. Well, what I noticed about angle C is that it intercepts this arc down here. But it's not the only angle that intercepts that arc. Angle D does also. Angle D measures 60 degrees. So if angle D measures 60 degrees, that means this arc measures 120. Which means angle C also measures 60 degrees. Two angles that intercept the same arc are congruent. So C is 60 degrees. The measure of arc AB we just said is 120 degrees. And then we've only got one arc left for the whole circle going all the way around, and that's arc AD. And so we can subtract all the rest of the arc measures from 360 to get AD. So that's 360 minus 120 minus 50 and minus 80. And that gives me 110 degrees for the measure of arc AD, which is right over here. All right, the last example on your guided notes, it says find the measures of angle A, B, and C. Well, this is actually a little interesting. This is kind of a blast from the past because angle A, it's really not angle A, the measure is A, but that's okay, we'll call it angle A. Angle A is a central angle. It's not inscribed because look at where the vertex is. It's right at the center of the circle. Central angles have the same measure as the arc. And then these two angles A and B is also a central angle, but A and B together make a linear pair, which means they have to add up to 180. So B is 180 minus 50, that's 130. And we just said B is a central angle, so looking at, just this. Looking at which arc B intercepts, it intercepts the arc with C on it. So if it's a central angle, it would be the same measure. So C is also 130 degrees. So that's just a reminder that central angles are also a thing. We have inscribed angles that we know about now, but central angles are also a thing. Last thing I want to show you here is that I made a little handy all-in-one-place note sheet for myself here by folding a paper into 4 squares, into 4 pieces, 4 portions, I guess, into a rectangle. And in the first quadrant of the paper, I wrote the inscribed angle definition and also talked about what an intercepted arc is. And then the first theorem, which is really the most basic, it's just saying that the angle measure for an inscribed angle is half of the arc measure. And then each of the other quadrants got its own theorem. Here's the one that says 2 angles that intercept the same arc are congruent. Here's the one that says if you have an inscribed angle that intercepts half the circle, then it's a right angle. We could go ahead and draw that on here. And then finally, a quadrilateral is in a circle if and only if its opposite angles are supplementary. So if you want to, that might be something for you to make to help you with this topic, which is inscribed angles. I hope this has been helpful. Enjoy working with inscribed angles and the rest of dealing with circles. It's a pretty big deal in geometry. See you later.